Okay, so I'm going to go through a few examples from the calculus option. We're going to look at continuous functions, L'Hopital's rule, and then the mean value theorem as well. Okay, so the first question we've got the weight in kilograms of a dog, and we're given a piecewise function with two parts between 0 and 5, and then for t greater than 5. First part simply says we need to find the value of c given that Wt is continuous. Okay, so for this we're using the fact that if it's continuous, the limit from the left hand side is going to be equal to the limit from the right hand side. So basically as we approach 5 for this function and as we approach 5 for this function, we should get the same answer. Okay, so all we need to do for that is basically put those values in. So I'm going to see what happens as t approaches 5 for this function. Well, obviously that's just going to become 2 plus c times 5, and equally as we approach 5 and this function, we're going to end up with 16 minus 35 over 5. Okay, so that will just give me some sort of equation, which is this one here. So 2 plus 5c, and that is equal to 16 minus 35 over 5. I just rearrange that to get c equals 7 over 5. Okay, so that's a relatively easy beginning part of this question, and the next 2 marks also pretty straightforward. It says write down the weight of the dog when bought from the pet shop. Well, if we just read the question carefully, t weeks after being bought from the pet shop, so therefore t is going to be 0 at the point that it's bought, and we put t equals 0 into this first equation because it's valid between 0 and 5, and we therefore get the weight of 2 kilograms. Okay, and then for the upper bound for the weight of the dog, we can substitute 7 over 5 that we found for c for the first equation, and then we've got this part for the second equation, and we can see quite quickly that the maximum value for this first one is if we put 5 into this first equation, and that's just going to give us 2 plus 7, so that's 9. So on the first part the maximum value is going to be 9, and then on the second part, well, it's never going to be more than 16 because we're doing 16 take away some number, and so obviously it could get closer and closer to 16 as the time gets ever larger. Therefore we can just say that the upper bound is going to be 16. Okay, and then the third part of this question gets a little bit more difficult. We've got to prove from first principles that Wt is differentiable at t equal to 5. And we're going to start with this basic idea here, that if it's differentiable, then the limit from the left hand side of the differentiated function is equal to the limit on the right hand side of the differentiated function. And also remember, when we're looking at first principles, what we're basically doing is we're finding the limit as h approaches 0 of f of, well, in this case here we're using t, so t plus h take away f of t all over h. Okay, so again, it looks slightly daunting at first, but if we just try and put some numbers in, so we say, well, what do we want to do? We want to basically replace, so we're going to look at the limits, this function here, we're going to replace t with t plus h. So let's do that in that first one. So 2 plus ct, we're going to replace that by t plus h, and then we're taking away f of t. So the limit of this function on the left hand side, well, we have 2 plus 7 over 5 bracket 5 plus h, just replace t with 5 plus h, and then take away 2 plus 7 over 5 times 5. Okay, because remember I'm looking at the point when t is equal to 5. If I then simplify this top line, I'm going to get 7 over 5 h over h. Okay, and then I can see, well, the h's are going to cancel, and therefore the limit on the left hand side of this differentiated function is going to be 7 over 5. I use the same idea to look at this second function. So again, I'm going to try and differentiate this function from first principles at the point for t is equal to 5 and see what happens. So this is my first part of the equation. So as before, I've replaced the t with 5 plus h, because I'm looking at the point t equals 5, and then I've replaced the t here just with the 5. So I get this function here, 16 take away 35 over 5 plus h, take away 16 minus 35 over 5. Hang on, that should be here, all over h. Okay, and then it's going to be the same as before, where I'm going to basically see what happens. So if I try and simplify this function, I will end up with, firstly with this thing here. So I've just expanded out the brackets, so I end up with minus 35 over 5 plus h plus 7 all over h. And then I try and make this all into one single fraction. So I'm going to times the top and the bottom of 7 by 5 plus h. So I get this thing. And then again I try and simplify this a little bit. And I end up with this. So minus 35 plus 7h all over 5 plus h all over h. And then like the minus 35 and plus 35, well, they're going to cancel out. And the h and the h here, they cancel out, so I end up with 7 over 5 plus h, and then I run h approaching 0, and then that's also going to give me 7 over 5. Okay, so I can just double check that. Look, so for both from the left hand side and the right hand side I've got 7 over 5, therefore I've proved from first principles that it's differentiable at t is equal to 5. Okay, next we're going to have a look at a few LHopital rules. The first one, so we've got tan x over x plus x squared, and we want to see the limit as x approaches 0. Well, the first thing we need to do is check that we can use LHopital for this, and yes, we've got a 0 over 0, so when x is 0, this gives the top of 0 and the bottom of 0. So we can use the LHopital rule, and that simply says that we can basically differentiate both the top and the bottom, and that will give us an equivalent limit to this first one here. So if we do that, we can use the formula book for this one. So the differential of tan x is in the formula book, and that gives us sec squared x. I differentiate the bottom part and get 1 plus 2x, and now I can just put x equals 0 into this. Well, that is 1 over cos squared x. X approaches 0, that's going to give me 1. And 1 plus 2x, again, that's going to give me 1. So therefore the limit for this function will actually be 1. Okay, so that's a 4-mark question. Next one is slightly more difficult, and we've got a clue here because it's worth 7 marks. So it's going to be probably slightly more difficult than the previous one. So we start off by checking that, yes, again, when x is equal to 1, we get a 0 over 0. Therefore, yes, we can use the L'Hopital's rule. And then I have to differentiate this function. I do so, and I also have to use the product rule here. So I differentiate minus x squared, gives me minus 2x. And then I use the product rule, so I keep the first function, differentiate the second function, and then differentiate the first function and keep the second function. That will give me this, if I remember that ln x will differentiate to 1 over x. On the bottom, minus sine pi x over 2 is going to give me this here, so pi over 2 cos pi x over 2. Again, I just simplify that and I get 4x ln x on the top and then this on the bottom. Unfortunately, if I then try and put x equals 1 into this, well, what happens? I still get a 0 equal to 0. Okay, so you're possibly expecting this because it's worth 7 marks, so you're probably expecting to have to do something extra. So, well, we try again. Basically, we do exactly the same thing. So one more time, we're going to differentiate both the top and the bottom, and yet again I have to use the product rule. So for x, ln x, I differentiate the first function, keep the second function the same, and vice versa. I end up with 4 ln x plus 4x 1 over x, and again I differentiate the denominator. We get pi squared over 4 sine pi x over 2, and this time, thankfully, when the limit of x approaches 1, I put 1 into this top and the bottom, and I end up with 16 over pi squared. So there we go, that is my limit for this function. Okay, and then a couple more quick ones for L'Hopital's rule. First off, we notice when it's written like this, sometimes they like to write it in a form where we can't yet use L'Hopital's rule. We've got to remember that we've got to write it as a fraction. So we can just rewrite x e to the minus x as x over e to the x. And now it's written like that, and I've got the limit of x goes to infinity. I've got the right sort of thing that I can use L'Hopital's rule, which is infinity over infinity. So that gives me the go-ahead to use L'Hopital's rule. And pretty easy, this one. I can just differentiate the top and the bottom. And there we go, as x approaches infinity, e to the x is going to get larger and larger. Therefore, we get ever closer to 0. So my limit for this one is going to be 0. And one more example of L'Hopital's rule where we have to create the fraction first. Once again, I basically just use algebraic fractions times the top and the bottom by sine x times the top and the bottom by x. And there we go, I'm going to get sine x minus x over x sine x. And now I can try, if I put x equals 0, yeah, I end up with 0 over 0. Again, I can use L'Hopital's rule. I differentiate it. Again, I need to use the product rule a little bit on the bottom one. And once again, if I put x equals 0, I once again end up with a 0 over 0. So one more time, I'm going to need to differentiate this function. And yet again, as long as you use the product rule correctly, you should end up with minus sine x on the top, and minus x sine x plus cos x. As x approaches 0, well, the sine x is going to become 0, the bottom is not 0, therefore the limit will just be 0. Okay, so sometimes just be careful to make it into a fraction first, and then follow L'Hopital's rule as you would do normally. And the very last question, I've chosen what was one on the mean value theorem, which is one of the new topics that they added about a year or so ago onto the syllabus. It can be quite nasty questions, and this is an example of a pretty tricky question, really. It's very easy to make a mistake on this question. It says we've got a continuous function, it's defined in a domain, and it's differentiable also on this domain, and we know that the differential of the function is positive, so we've got an increasing function. And then we've got to use the mean value theorem to prove that any x and y belonging to this interval, to this domain, and if y is greater than x, then f of y is greater than f of x. Okay, so it looks pretty complicated. The first thing to say is, well, what is the mean value theorem? It's basically this thing here, f dash of x is equal to f of b, take away f of a, over b minus a. And we kind of look at, maybe this kind of graph helps a little bit. So here we go. It's basically just saying that if we've got a point A and a point B, and we work out the gradient between those 2 points, then there will be another point on this function in red between these 2 points here that will also have the same gradient. So if we work out the gradient between A and B, there will be another point C that also shares that gradient. That's basically what it's saying. We're working out the gradient by doing f of b minus f of a over b minus a. Okay so far, but this is where the question gets a bit confusing, because they've used an x and a y, so they're actually using y as part of the domain for this question. The y is not part of the y-axis, the y is part of the domain. We're saying x and y belong to this domain between a and b. So the domain is basically saying we can choose any x's and y's that belong to kind of our chosen domain. So this is why it's confusing. And also we're going to try and show that this point C between these 2 points here. Okay, so we put that information into our equation here. So we've got f dash of C, so this is the sum point that we're looking at. So the sum point that's between the 2 domains, and we've kind of relabeled the graph, so we've got basically f of y take away f of x over y minus x. We're still doing the same thing. We're still finding the gradient of the line between x and y, and we're still trying to show that the sum point between these 2 values on this point of C, which has the same gradient. Okay, so this is what we should write. Once we've got that, well, we know that this value here, f dash of C, which is f of y minus f of x over y minus x, this must be greater than 0 because the differential is greater than 0, so it's an increasing function. Therefore, C is in that domain. Therefore, it must be positive. Okay, so that's our first point to note. And then we also have to note that, look, well, y is greater than x. My sketch was just giving me there, y is greater than x. Therefore, when I do y take away x, that must be greater to 0. So I've got now a function where I know this whole function here is greater than 0. And I know that the bottom part, the denominator, is also greater than 0. Well, the only way that that is possible is if the numerator, f of y minus f of x, is also greater than 0. And there we go. Don't worry if you find that particular question quite difficult. Sometimes the examiners do kind of throw in nasty questions just to kind of trick you. But there we go. I hope that was of some use.